The Mars window of late 2026, humanity's defining moment. In the closing months of 2026, an event will unfold that could fundamentally alter the trajectory of human civilization. A launch window to Mars will open, a fleeting period when Earth and the red planet align in celestial geometry favorable for interplanetary travel. This astronomical phenomenon occurs only once every 26 months, transforming each occurrence into a high-stakes competition among the world's spacefaring nations and private entities. The physics governing interplanetary voyages impose unforgiving constraints. Both Earth and Mars follow elliptical orbits around the Sun, their paths tracing complex patterns through three-dimensional space. The optimal transfer window, when the energy required for transit reaches its minimum, persists for merely a few weeks. Missing this opportunity means waiting another 2 years and 2 months before conditions align again. This temporal bottleneck explains why every major space agency synchronizes their most ambitious missions with these rare windows. The China National Space Administration has invested billions in preparing the Tianwen-3 mission, an undertaking that represents the most technically demanding endeavor in their space program's history. Following the remarkable success of their Zhurong rover, which touched down in Utopia Planitia in May 2021, Chinese engineers have designed an intricate two-stage sample return architecture. The first spacecraft will execute a powered descent to the Martian surface, deploy a sophisticated drilling mechanism capable of collecting subsurface samples from depths of 2 meters, and launch a return vehicle into Martian orbit carrying hermetically sealed containers of Martian regolith. A second orbiter will rendezvous with this ascent vehicle in orbit around Mars, capture the sample container, and begin the 7-month journey back to Earth. The entire operation spans approximately 3 years from launch to sample delivery. The United Arab Emirates Space Agency, having established their credentials with the successful Hope orbiter mission that reached Mars in February 2021, now pursues an even more ambitious objective. Their planned mission to the asteroid belt will utilize a gravity assist maneuver at Mars, using the planet's gravitational field to accelerate their probe toward its ultimate destination in the main asteroid belt between Mars and Jupiter. This trajectory demonstrates sophisticated orbital mechanics and positions the UAE as a serious player in deep space exploration. The probe will conduct close flybys of 7 asteroids over a 5-year journey, collecting spectroscopic data that will illuminate the early history of our solar system. NASA's contribution to the 2026 launch window centers on the next critical phase of the Mars sample return campaign, developed in partnership with the European Space Agency. The Perseverance rover has been methodically collecting core samples of Martian rock and sediment since February 2021, carefully selecting specimens from locations that represent different geological epochs and environmental conditions. Each sample undergoes meticulous documentation, photographed from multiple angles, analyzed with onboard spectrometers, and sealed in titanium tubes specifically engineered to prevent contamination and preserve the geological record. The 2026 window is essential for launching the Sample Retrieval Lander and the Earth Return Orbiter, the 2 spacecraft that will collect these precious samples and transport them to terrestrial laboratories where instruments far more sophisticated than anything that can be sent to Mars await their arrival. But the most intense scrutiny and public fascination centers on SpaceX and their Starship system. Elon Musk has publicly committed to launching the first cargo missions to Mars during the late 2026 window, declaring this timeline repeatedly in interviews, shareholder meetings, and social media posts. These will be uncrewed technology demonstrators, designed to validate the ability to land a super-heavy payload on the Martian surface and survive the harsh conditions long enough to prove the viability of the architecture. Starship was conceived from its inception as a Mars transport system. The fully stacked vehicle stands 120 meters tall, taller than the Statue of Liberty from ground to torch. The spacecraft itself, the upper stage that actually travels to Mars, measures 50 meters in length and 9 meters in diameter, providing an internal pressurized volume of approximately 1,000 cubic meters. For interplanetary missions, Starship can deliver over 100 metric tons to the Martian surface. To appreciate this capability, consider that the Perseverance rover, one of the most sophisticated machines ever sent to another world, weighs just over 1 metric ton. Starship can deliver the equivalent of 100 Perseverance rovers in a single mission. This order of magnitude increase in payload capacity fundamentally changes what missions become possible. The technical challenges of landing Starship on Mars differ dramatically from any previous landing system. Mars presents a uniquely difficult environment for powered descent. The atmosphere, composed primarily of carbon dioxide at a pressure averaging 600 pascals, less than 1% of Earth's sea level pressure, provides insufficient density for parachute-based landing systems to effectively slow a massive vehicle. Yet this thin atmosphere generates enormous heating during hypersonic entry, with shock layer temperatures exceeding 2,000 degrees Celsius. Starship must employ a sophisticated combination of aerodynamic deceleration using its body as a lifting surface, followed by a propulsive landing burn using its Raptor engines. The selection of Raptor engines burning liquid methane and liquid oxygen represents a strategic choice driven by Mars mission requirements. Methane can be synthesized on Mars through the Sabatier reaction, combining carbon dioxide from the Martian atmosphere with hydrogen derived from subsurface water ice. The reaction produces methane and water, with the water then electrolyzed to yield more hydrogen and oxygen. This in situ resource utilization eliminates the need to transport return propellant from Earth, reducing mission mass by hundreds of tons and making economically sustainable Mars operations feasible. A small nuclear reactor or extensive solar array could power this chemical plant, gradually filling Starship's propellant tanks over the 18 to 20 months it remains on the surface waiting for the return window. The cadence of Starship test flights during 2024 and 2025 will determine whether the 2026 Mars launch remains achievable. Each orbital test flight generates terabytes of telemetry data, temperature readings from thousands of sensors embedded in the heat shield, structural loads measured during atmospheric re-entry, engine performance parameters during the landing burn, propellant slosh dynamics in the massive tanks. SpaceX engineers analyze this data to refine their models, identify failure modes, and iterate on the design. The heat shield alone represents an enormous engineering challenge. Composed of thousands of hexagonal ceramic tiles, each approximately 15 centimeters across, the thermal protection system must survive both Earth re-entry at 11 kilometers per second and Mars entry at 7 kilometers per second, with completely different atmospheric compositions and entry profiles. The trajectory to Mars follows what orbital mechanicists call a Hohmann transfer orbit, named after the German engineer Walter Hohmann, who described it mathematically in 1925. This represents the most energy-efficient path between two planets orbiting the same star. The spacecraft accelerates from Earth orbit, raising its aphelion, the farthest point from the Sun, until it intersects Mars's orbital path. The timing must be exquisitely precise. Mars must be in exactly the right position when the spacecraft arrives, months after launch. Miss that target by even a few days, and the spacecraft flies past into deep space with insufficient propellant to correct course. The journey duration varies depending on the specific orbital geometry of each window, typically ranging from 6 to 9 months. During the 2026 window, the transfer time will be approximately 7 months. This months-long transit through interplanetary space subjects the vehicle and its systems to an environment far harsher than low Earth orbit. Beyond the protective cocoon of Earth's magnetosphere, cosmic radiation from distant supernovae and solar energetic particles from our own star bombard the spacecraft continuously. Galactic cosmic rays, composed primarily of high-energy protons and atomic nuclei, can penetrate deep into materials, damaging electronic components and presenting long-term health risks to future crews. Micrometeorites, traveling at relative velocities of tens of kilometers per second, pose an impact hazard. Temperature extremes challenge thermal management systems. Surfaces facing the sun heat to over 100 degrees Celsius while those in shadow plunge below -100 degrees. The initial cargo missions will carry relatively modest payloads optimized for technology demonstration rather than maximum utilization of Starship's capacity. Likely manifests include power generation systems such as solar arrays or compact nuclear reactors, test articles for propellant production equipment, weather stations to characterize local conditions at the landing site, and perhaps experimental systems for extracting water from Martian soil. The primary objective is demonstrating the complete mission profile: launch from Earth, transit to Mars, entry into the Martian atmosphere, power descent, and long-term survival on the surface through multiple day-night cycles and seasonal variations. The Martian surface environment presents formidable challenges for any hardware. Temperature swings are extreme. The equatorial regions might reach a pleasant 20 degrees Celsius during summer afternoons, but plunge to -80 degrees at night. Polar regions routinely experience temperatures below -125 degrees Celsius, cold enough to freeze carbon dioxide out of the atmosphere, forming seasonal polar caps of dry ice. Global dust storms, which can envelope the entire planet for months, reduce solar power generation and coat surfaces with fine, abrasive particles. The dust itself, composed of iron oxide and silicate minerals, exhibits unusual electrostatic properties due to the absence of moisture, clinging to surfaces and potentially infiltrating seals and mechanisms. The scientific community watches this convergence of missions with profound interest that transcends the geopolitical competition. Mars holds critical clues to questions that touch on our understanding of planetary evolution, the potential for life beyond Earth, and the long-term habitability of terrestrial worlds. Geological evidence accumulated over decades of robotic exploration paints a compelling picture of a planet that once possessed conditions far more Earth-like than the frozen desert we see today. Valley networks carved by flowing water, delta deposits where rivers once emptied into standing bodies of water, hydrated minerals that could only form in the presence of liquid water, all indicate that during the Noachian period, roughly 3.5 to 4 billion years ago, Mars had a substantially thicker atmosphere and liquid water persisted on its surface for extended periods. What caused Mars to lose its atmosphere and transform into the cold, dry world we observe today? Current theory points to the loss of the Martian magnetic field approximately 4 billion years ago. Without this protective shield, solar wind gradually stripped away the upper atmosphere over hundreds of millions of years. Understanding this process has implications beyond Mars. It informs our understanding of planetary habitability throughout the galaxy and helps identify which exoplanets might retain their atmospheres long enough for life to develop. Did life arise on Mars during that earlier, more hospitable epoch? The question drives much of Mars exploration. If life emerged independently on Mars, it would suggest that life arises readily wherever conditions permit, with profound implications for the prevalence of biology throughout the universe. If we find evidence of extinct Martian life, the question becomes whether it shares a common origin with Earth life. Perhaps both planets were seeded by meteorite impacts that ejected life-bearing material during the late heavy bombardment period, or whether it represents a truly independent genesis, a second origin of life in our solar system. Each new mission advances our ability to answer these questions. The samples that China's Tianwen-3 and NASA's Mars Sample Return Program aim to deliver to Earth will enable analyses impossible to conduct remotely. Terrestrial laboratories house instruments weighing tons, consuming kilowatts of power, and operating with precision that requires vibration isolation and ultra-clean environments. Mass spectrometers capable of measuring isotope ratios to parts per billion, electron microscopes that can image individual organic molecules, equipment for dating rocks to within millions of years of their formation age. These tools will scrutinize Martian samples atom by atom. The 2026 launch window also serves as an essential proving ground for technologies that must function flawlessly before humans can safely travel to Mars. Every uncrewed mission tests systems that will eventually support human crews. Precision landing systems must reliably deliver spacecraft to predetermined locations, not just somewhere on Mars, but to specific sites selected for their scientific value or proximity to resources. Communication systems must maintain contact across vast distances with minimal power consumption. Automated systems must handle contingencies without real-time input from Earth, since communication delays range from 3 to 22 minutes one way depending on the relative positions of the planets. This communication lag fundamentally alters mission operations compared to missions in Earth orbit. When controllers operate the International Space Station, they communicate in near real time, responding immediately to any anomaly. On Mars, by the time controllers see a problem and send a command, over 40 minutes might have elapsed, an eternity during a crisis. Consequently, Mars missions require sophisticated autonomy. Spacecraft must detect failures, implement contingency responses, and in some cases execute entire landing sequences without human intervention. The competition among different space programs creates a dynamic that accelerates technological advancement. When China successfully landed Zhurong on Mars, demonstrating their capability in precision entry, descent, and landing, it validated their deep space technologies and spurred Western programs to maintain pace. When SpaceX demonstrates routine reusability of super heavy boosters, catching them with mechanical arms and relaunching within weeks, it forces traditional aerospace companies and government agencies to reconsider their approaches to space access. This healthy competition benefits everyone. More missions means more data means better understanding, and better understanding accelerates progress toward sustainable Mars exploration. Economic considerations increasingly influence mission planning and architecture design. The cost of delivering mass to Mars has been a primary limiting factor in mission scope. Traditional expendable launch vehicles might cost $200 million per launch with payload capacities to Mars measured in single-digit tons. At these prices, only governments could afford Mars missions, and only sparingly. SpaceX argues that fully reusable launch systems can reduce costs by orders of magnitude. If Starship can be reflown with minimal refurbishment, and if orbital propellant depot technology enables efficient refueling in Earth orbit, they project launch costs could drop to single-digit millions of dollars per flight with payload capacities exceeding 100 tons. Mars represents more than scientific curiosity or technological challenge. It serves as a testbed for technologies and techniques essential if humanity is to become a multiplanetary species. Establishing a self-sustaining settlement on another world requires solving problems at the intersection of multiple disciplines. Life support systems must recycle air and water with extreme efficiency. Agriculture must function in reduced gravity with artificial lighting or filtered sunlight. Medical care must function without possibility of evacuation to Earth for at least the 26 months between launch windows. Martian gravity. At 38% of Earth's surface gravity, falls between the Moon's 16% and Earth's 100%. This partial gravity regime remains largely unexplored from a human physiology perspective. Decades of research on the International Space Station have thoroughly documented the effects of microgravity on human physiology: bone density loss of 1 to 2% per month, muscle atrophy despite rigorous exercise protocols, cardiovascular deconditioning. Will Mars gravity be sufficient to prevent these degenerative changes? These questions must be answered through research before committing to permanent settlements. The Martian day, called the Sol, lasts 24 hours and 39 minutes, remarkably close to Earth's rotation period. This near match simplifies many aspects of human adaptation. Circadian rhythms evolved over millions of years to match Earth's day-night cycle, and most humans can easily adjust to the slightly longer Martian Sol. The Martian year, however, spans 687 Earth days, nearly twice as long. Seasonal changes occur more gradually, but with greater extremes due to Mars's more eccentric orbit and lack of moderating oceans. Launch operations during the 2026 window will likely commence in October and extend through December. The precise launch dates for each mission depend on the specific target orbit and landing site on Mars. Earlier launch dates in the window allow shorter transit times but require more energy. Later dates reduce energy requirements but extend flight duration. Mission planners balance these trade-offs against spacecraft capabilities, acceptable risk levels, and scheduling constraints. Multiple launch sites will support the 2026 missions. The Jiuquan Satellite Launch Center in the Gobi Desert will host Chinese launches. Cape Canaveral Space Force Station and Kennedy Space Center in Florida will support NASA and potentially commercial missions. SpaceX's Starbase facility near Brownsville, Texas, will handle Starship launches if the site receives regulatory approval for orbital missions. Each facility has unique capabilities and constraints. Proximity to the equator provides a launch velocity bonus, range safety requirements limit launch azimuths, and environmental regulations vary by jurisdiction. The risk of failure on missions of such technical complexity remains substantial despite decades of experience and advancing technology. The history of Mars exploration soberly reminds us that success is never guaranteed. Of the 49 attempted missions to Mars through 2024, only 28 achieved their primary objectives. Mars has earned its reputation as a challenging destination. The Soviet Union suffered a string of failures in the 1960s and 1970s. NASA's Mars Observer vanished just before orbital insertion in 1993. The European Space Agency's Beagle 2 lander reached the surface but failed to deploy its solar panels in 2003. Yet these risks and difficulties amplify the significance of successes. Every successful landing represents hundreds of correct decisions, thousands of hours of testing, and alignment of variables beyond human control. Each success expands the envelope of demonstrated capability and pushes the boundary of what the next mission might attempt. The learning curve in Mars exploration trends upward. Each mission builds on lessons from previous attempts, and success rates have improved over time as experience accumulates. The scientific instruments flying to Mars in 2026 represent the current state of the art in planetary science technology. Spectrometers using laser-induced breakdown spectroscopy can vaporize small amounts of rock and analyze the light emitted to determine elemental composition. Ground-penetrating radar can image subsurface layering to depths of hundreds of meters, searching for buried ice deposits. Meteorological packages measure temperature, pressure, humidity, wind speed, and direction, building a comprehensive climatological record. Seismometers detect Marsquakes and meteorite impacts, using seismic waves to probe the planet's internal structure. The InSight lander, which operated on Mars from 2018 to 2022, demonstrated the power of seismology for planetary science. Its seismometer detected over 1,300 Marsquakes, ranging from magnitude 1 to magnitude 5. Analysis of seismic wave propagation revealed that Mars has a liquid outer core with a radius of approximately 1,800 kilometers, larger than previously estimated. These findings transform our understanding of Martian geophysics and inform models of the planet's thermal evolution. Parallel to preparations for 2026 launches, research and development continues on technologies for subsequent mission windows. Advanced solar cell designs optimize efficiency at Mars's lower solar intensity. The planet orbits 50% farther from the Sun than Earth, reducing solar energy density to about 43% of that at Earth. Small fission reactors specifically designed for space applications promise reliable power generation independent of solar conditions. NASA's Kilopower project tested a reactor design that produces 10 kilowatts of electrical power from a uranium core the size of a paper towel roll. Scaling this technology could enable energy-intensive operations like propellant production. Water extraction from Martian regolith receives intensive research attention. Mars contains substantial water ice, but accessing it requires techniques adapted to Martian conditions. In polar regions and at higher latitudes, ice exists within the top meter of soil. Various approaches are under investigation: resistive heating of soil, microwave heating that selectively couples to ice, chemical extraction using salts that absorb moisture. Demonstrations of these technologies on actual Mars missions will determine which approaches prove most practical. International cooperation in Mars exploration remains complex. Scientific collaboration continues despite geopolitical tensions. Researchers from different countries co-author papers, share data from spacecraft instruments, and coordinate observations. After a limited proprietary period, mission data becomes publicly available through planetary data archives. This enables scientists worldwide to conduct research regardless of which agency flew the mission. Yet national prestige and strategic competition drive much of Mars exploration. Countries pursue Mars missions partly for the international status they confer. Successfully landing on Mars demonstrates technological sophistication that translates to broader capabilities. The competition for firsts motivates aggressive timelines and ambitious mission designs. Who will be first to return samples from Mars? Who will demonstrate in situ resource utilization at scale? These questions carry weight beyond their scientific merits. The 2026 window could mark an inflection point in Mars exploration, the moment when human presence on Mars transitions from aspiration to concrete near-term objective. If SpaceX succeeds in landing Starship on Mars, it validates the architecture for eventual human missions. If the sample return missions succeed, it proves the technical feasibility of round-trip missions. If multiple missions from different countries operate simultaneously on Mars, it establishes Mars as a destination for sustained international presence. Technologies developed for Mars have terrestrial applications. Efficient recycling systems designed for spacecraft benefit environmental sustainability on Earth. Remote medical capabilities developed for astronauts improve healthcare access in isolated regions. Autonomous systems that enable spacecraft to operate without real-time human control translate to applications in autonomous vehicles and industrial automation. The generation of scientists and engineers currently in training will build on the foundation established by 2026 missions. Students today studying aerospace engineering, planetary science, and robotics might become the mission controllers and astronauts of the 2030s and 2040s. Some of them will likely walk on Mars, establishing the first permanent human settlements on another planet. The technologies proven on cargo missions become the building blocks for human missions. As launch dates approach, the pace of final preparations intensifies. Spacecraft undergo final testing in thermal vacuum chambers that simulate space conditions. Flight software receives exhaustive verification. Launch vehicles are assembled and propellant loading procedures are rehearsed. Mission control teams conduct simulations, practicing responses to every conceivable scenario. Public interest in the 2026 missions will likely spike as launches approach. Mars has captured human imagination for centuries. Modern Mars exploration combines cutting-edge technology with age-old human curiosity about our neighboring world. When missions launch, especially high-profile attempts like SpaceX's Starship, media coverage will be intense. Success would generate enormous enthusiasm for continued space exploration. Failure would prompt questions but also determination to learn and try again. The months following the 2026 launches will be tense for mission teams. During the cruise phase, spacecraft require monitoring and occasional course corrections. As Mars approach begins, activity intensifies. Navigation teams refine trajectory knowledge. The final hours before landing are among the most stressful moments in any space mission. Communication delays mean that by the time controllers see telemetry confirming landing sequence start, the spacecraft has already landed or crashed. Its fate was sealed minutes earlier. Success brings celebration but also renewed responsibility. A spacecraft on a Martian surface represents the beginning of its primary mission. Systems must be checked out, instruments calibrated, and scientific observations begun. For landers and rovers, the surface mission might continue for years. For sample return missions, the surface phase is one step in a multi-year campaign. Looking beyond 2026, the cadence of Mars missions will likely accelerate. Each window brings more missions as costs decrease and capabilities expand. The 2028 window might see human precursor missions. The 2030 or 2033 window could potentially host the first crewed mission. By the 2040s, multiple crewed missions might operate simultaneously, establishing a permanent research station. This vision raises questions extending into philosophy, ethics, and governance. Who has authority to establish settlements on Mars? How will resources be allocated? The Outer Space Treaty of 1967 prohibits national appropriation of celestial bodies, but may not adequately address commercial operations and permanent settlements. International dialogue on these issues has begun but remains far from consensus. The race continues, and the finish line constantly recedes as we achieve each milestone and set new goals. Mars transforms from a distant point of light into a real destination where humanity's future may acquire a new dimension. The 2026 launch window represents not an ending but a beginning, the opening of an era when multiple worlds host human activity, when interplanetary travel becomes routine, and when the survival of human civilization no longer depends on the fate of a single planet.